Hello everyone. Today we are going to talk about machine learning projects, especially for the course of Introduction to Machine Learning by Pacmann. The title of this project is IBRD Guided Scorecard Predictive Engine. And let's start. The outlines of this presentation will be the number one is the dataset and features, where we take a closer look at our datasets and find insights. And the number two is the methodology we use in this project, where we finally learn about logistic regression used in this project. And the number three is the experimentation of the projects. Alright, this is my introductions. My name is Hardeva Raghunando. I am currently working as a data scientist at an AI enabler startup. And here are my GitHub and LinkedIn account. And also feel free to follow and well, maybe we can connect to each other. Okay, the number one first, first thing first, the number one is the dataset and features, where we see the sneak peek of our dataset and make features out of it. Well, before we proceed further into our projects, it's better that we understand about the scorecard. What is a scorecard? Scorecard are decision-making tools used in various industries, including finance. Well, they help to evaluate and compare different aspects based on certain predefined metrics. And maybe you are wondering, like, why we use a scorecard? Well, scorecard provide a standardized way to assess risk. They convert complex data into simple score, aiding in making informed decisions. So it will be much easier to predict. Not really a predict. It will be much more easier to know whether this loan or maybe whether this borrower will be defaulted or not. Well, just to some kind of we can I don't know we can know whether someone will be bad or a good borrower like that. Well, you get the idea. Okay, our dataset, the source of our dataset is from the World Bank Open Data, and this dataset that they use in this project is last updated at June 21st, 2023. The shape of our dataset is with 9,012 rows and 33 columns, and the column types of our dataset, most of it are just administrative dates of the loans. And let's go to the data preparation. Well, this is where we clean the data by dealing with missing values appropriately. And our case, any column with more than 50% missing values is dropped, as they aren't adding much information to our journey. Well, actually, there are two scenarios that I check here. The first one is the null values. Well, the column that have no values at all, and the other one is the where we check about the zero values across all the data sets. Well, if it's more than 50%, maybe we can just drop it as it is. Okay, the next one is the exploratory data analysis. Well, this is where we explore the global distribution of loans using this world map. Each country is colored according to the number of loans it has received. This broad view helps us understand the geographical spread of our data. Actually, this will help us more when we're doing the features engineering and feature spinning. Let's continue. Okay, this is where we take a closer look at the loan distributions within some different regions. Some regions might have more loans than the others, and this could be significant in our journey. And by the way, this will be one of our features that we will use in our projects. Let's proceed. Now, let's take a look at the distribution of loan statuses. Each status provides us with different insights into repayment of the loan, giving us clues about the good and bad. And from these features, from these columns, we can proceed to separate the loans, whether is it good or bad. All right. From the loan status, we create labels for our loans. Loans that are fully cancelled or terminated are labeled as bad, and the fully repaid loans are labeled as good. Well, this labeling will guide us in our model predictions. Well, you might be wondering, like, why can't we just accept all of it? Well, the most of them are still ongoing loans, and that's why we can't really decide whether this loan is good or bad. I think it's more intuitive if we only choose the loans that have already been finished, like the one that have been cancelled or terminated, or maybe the one with full repaid status. Let's go. Well, this is where we doing the features engineering. Actually, there are two methods that mainly I use here. The first one is the wake of evidence. The wake of evidence actually help us to understand the predictive power of each features. within the each category within the features. It's like a compass getting us to valuable categories. Well, we can actually make the weight of evidence for all features, and then after we got all the weight of evidence, we can make a information value out of it. And an IV, or information value, quantifies the amount of information each feature brings to the models. That's why actually the part of information value we can some kind of, well, we can choose like whether this features is important enough or not, like that. Well, you get the idea. And you can see from this slide, actually this is the formula that I use to do the count of weight of evidence and information value. By the way, if you want to know more about the code, you can go to my GitHub account and I will put the link in the description below. So yeah, you can see by yourself. All right. And well, this is an example of the demonstration of weight of evidence and information value of one of our features. Well, actually, understanding this value help us to fine-tune the models and predict more accurately by binding the features into categories. From this example, it's actually from the features region where we can see this is the one that we already bin. Uh, Before this graph, actually there are more like kind of hard to explain, like the weight of evidence. I'll give you something to think like this. uh the higher the weight of evidence, the more likely the bad will occur. The less is the other one, right? So the intuition from this graph, actually, the higher the weight of evidence means that the bin, or the data that gets sorted into that bin, will have more risk than the other data that have been sorted in the lower bins with the lower weight of evidence. Well, yeah, you get the idea. Well, let's continue to the methodology. Well, this is where we look how our logistic regression works with our projects. All right, this is the formula of our logistic regressions. W, or our dependent variable. Well, it's the outcome of our models. This is what we are going to look at. This is the main course, the main, uh, I don't know what to say, the main target that we are looking for. This is the bad or good prediction. Actually, the W, I mean the Y is, well, well, you can say like the probabilities that we can get from the formula of the logistic regressions. And B0 is the y-intercept. This is where our starting point is, and B1 is the slope, the direction and steepness of our models. And the X1 is our features. So yeah, we'll get a lot of X1, by the way. It depends on how many features that we use in the models. And the E1 is the random error terms. And this is where we took uh like the most, yeah, well, we can say like it's the most important part in our models, in our modelings, where we from logistic regression we can take the log odds or log it from the formula, and based on this log odds and logit, we can make the we can make the logit and convert it into a score. That's why scorecard mostly in banks and many other financial institutions, sometimes they only accept algorithm that can export, or maybe algorithm that can explain more about the odds of something happening or not. Well, you get the idea. Since there are some algorithm like tree-based algorithm that we can't really decide uh, the odds possibilities of some certain things happen. Well, that's why the logistic regressions, or maybe the uh, linear algorithm uh, can do most of these problems. Well, you get the idea. All right. Since I said, like I said before, the logistic regressions output are the probabilities. Well, if you plot the probabilities in the sigmoid function in the logistic regressions, well, the as you can see in the graph, that the sigmoid function created an S-shaped curve. On this curve, you can see the dots of 0 and 1, where the 0 means good and the 1 means bad. Yeah, with the sigmoid function, our legacy regression model is fully equipped to predict whether a load is good or bad based on the probability. Well, as you can see from the y-axis, we can see that there are numbers like zero point 0.0 or maybe zero point 0.4 and zero point 0.8. That's where the probability we get from the models. And the dots that you can see from the below part and the upper part is like the one with the upper part is the one labeled 1 and the lower part is the one where we labeled as 0 or good. Well, based on the sigmoid function, we can plot the probability and we can like somehow we not somehow well we can uh, plot the probabilities and we can set the threshold that we want to predict like whether it will be good or bad based on this threshold from the sigmoid function. Well, I hope you understand. All right, this is for the experimentation of how our model works so far. The first one is the baseline model matrix. Our baseline models provides us with a starting point. Well, since these baseline models don't have any other metrics used, it's just well, some people say it's a vanilla model where there are no parameters added, where it's just as it is. The models, yeah, well, you can say it's a simple model. Despite its simplicity, it's able to make some correct predictions. However, it struggles to correctly identify bad loans, marking an area of improvements. Well, if you can see from your right side, here, yeah, over there, yeah, we can see that the baseline models and in train set it play much more better than the one from the test models. If you see from this, oh, I'm sorry. If you see from this, yeah, yeah. If you see from this graph, from this table, you can see that there are actually the several metrics. You can see like the precision, the recall, F1 score, accuracy, and ROC. You can see that the train and test models, the train plays way better than the test models. Well, as we can see from there, that the baseline models is still overfitting to our models. Well, maybe you'll ask like, what is overfitting? It's where the model is too fitted to the train set that they don't understand. They don't know the difference if we give them something new from the test data set. So, well, if you can say like a bed, supposedly a bed is shaped like a square, but when a person sleep on top of the bed starting to shape like the person, right? Yeah, and when the bed only shape like the person and no other person can sleep on top of that bed anymore, that means that the bed is overfitting. Well, yeah, it may be fun. It's quite real, but well, you get the idea. All right. To overcome this overfitting things, I use the Bayesian search cross validations, where actually Bayesian search is a smart strategy we use to select the best settings. The algorithms can learn from past mistakes to make better future decisions. This is the Bayes variance trade-off. Well, as you can see from here, the training score and the cross validation score is well, kind of overlapping to each other, but yeah, the train score is still higher than the cross validation score, which indicates even though we have already doing the Bayesian search cross validations, the model still overfitting a little bit. And also about the cross validations, we use a 5-fold cross validations as it provides a good balance, not too small to be meaningless and not too big to be computationally heavy. All right, this is the fine-tune model metrics. The metrics table show us that the models improve performance, notably from here. Yeah, from here. The F1 score, balance of precisions and recall, is slightly better, and the AUC ROC, indicating that the model's ability to distinguish between class has also improved. And you can see that from the fine-tune test confusion matrix, we can see that there are increase in the true negative predicted by the models, where the first one is only 7, now we got 11. Well, maybe not much, but it's an improve, right? All right, the conclusions. We predicted loan risk using logistic regression. Our baseline model provided a good starting point, but still overfitting. Well, I think it's a good start though. With Bayesian search cross-validation, we improve its ability to identify bad loans. Although the accuracy of our fine-tuned model is slightly less, it excels in distinguishing between good and bad loans. And it's an important factor for our problems. And also for future works, we can gather more data for a more balanced dataset. Oh yeah, maybe you were wondering like why I don't use the oversampling or maybe undersampling the data. Well, like I said before, in the binding section in the feature engineering, we need to see the actual trend of the data. And if we do the oversampling or maybe we do the undersampling, we can't really see the uh, trend of the data, which will make it even more well, which will make it undersample. I mean, underperform than the overfitting data. Well, that's why we don't do the sampling techniques. All right, let's go to the future works again. We can try to experiment with other feature engineering techniques and models. Leverage advanced techniques like ensembling learning or deep learning for better predictions. Well, ensemble learning might works, but well, that's another project for the future. And the last part is where we develop our model further for real-time predictions through an API. All right, that's from me. If you have any questions, leave a comments down below. And well, you can also read my article on Medium. I will give the description below. And see you on the next slide. Bye bye.